Hello everyone, I'm Xiao from the University of Edinburgh. Today I'm going to show you how can we learn a segmentation model from multiple source domains. It can generalize well to new unseen domains and most importantly can be trained when there are only few labeled samples. I'll first introduce the problem and also the motivation. So for medical image segmentation, we collect data from medical centers, and we analyze those data with deep models to predict the segmentation mask. There are actually practical challenges for traditional segmentation models due to domain shifts across datasets. Usually, the performance reduces a lot on unseen datasets, and this means those models have poor generalization ability. So for domain shifts, when we collect data from multiple centers, they use different scanners and also different people go to different medical centers. This means there will be imaging variation caused by different scanners and scanner acquisition settings. Also, the anatomical structure variation because of different populations, and there will be different anatomy shape and pathology. And you can see here for different scanners and different patients, the changes between the images. The logical solution is to collect data from all scanners and sites and populations to cover all the variations. But we know it's impossible. So domain-generalisation as a solution to address the domain shifts, it considers multiple source domains and no information of the target domain is available. Also, domain generalization aims to learn generalized models for unseen domains. This is very applicable and challenging in medical applications. Previously, we tried to use content-style disentanglement, which is based on SDNet, to approach this problem. So, SDNet, we have an image, and there will be two encoders to encode the anatomy factor and modality factors. And using the anatomy factor, we can predict the segmentation mask. Combining the modality factor and anatomy factor, we can reconstruct the original image. And you can see in the decoding path, it's unsupervised, so we can train this model in a semi-supervised manner. We actually have a tutorial dream at MICCAI 2021, so feel free to check a bit about disentanglement. So we augmented the latent space to generate new images. I hope the model could generalize well to new domains as a solution of domain generalization. As you can see here, we pre-train an SDNet to extract the factors from 3 source domains. And we randomly sample the factors and mix them to generate new images. Hopefully the augmented data will cover the unseen domain. However, when the unseen domain has novel anatomy and modality, this method will fail. So, what about more advanced strategy for domain generalization? Well, meta-learning is one of the most popular ones. There is a feature extractor and also a task network in meta-learning framework. So, meta-learning for domain generalization, it aims to mimic the training and the test scenario. By constructing meta-train and meta-test for every iteration. So you can see the source domains here are split into meta-train and meta-test. And when we update the model, we wish the updated weights to perform well on the meta-test set. We can measure it with meta-test loss, also the meta-train loss for the meta-train domains. So we updated the weights of the original model by using the two losses. And in this case, the model is trained to perform well on the meta-train and also meta-test sets. So, but all the previous meta-learning models, they are fully supervised. You can see here with extensive annotation, meta-learning works. But when in a low annotated data region, meta-learning could fail. So for semi-supervised meta-learning, we can integrate disentanglement to extract the factors of variation and use meta-learning to learn the shifts of disentangled representations in a semi-supervised manner. So about our method, So semi-supervised method learning, we aim to integrate the disentanglement. We want to learn representations from unlabeled data. So how do we design it? Well, it's very important to learn complete and sufficient representations. So first of all, we want to have the content representation for segmentation, the anatomical features side. Also, we have multiple multi-domain data, so we have two style representations, COM style and the domain-specific style. So we have three encoders to encode the three representations, and the domain-specific style should be discriminative, so we further encode it to extract the domain class. And we have a decoding path, which is unsupervised, to combine all of the factors to reconstruct. So we have unlabeled data, labeled data, and also meta training step and meta test step. For meta training step with labeled data, definitely we can disentangle and we can do the segmentation. But for unlabeled data, we can only do disentanglement. For meta test, with labeled data, we can do segmentation, but we can only do the proxy of disentanglement. Also, for the meta test and unlabeled case, we only have the proxy of disentanglement to train the model. Check the paper for more details of the losses. For the experiment, well, we choose two tasks. One is the cardiac image segmentation, MMS dataset. There are 4 domains. Also, spinal cord segmentation. There are also 4 domains. For baseline model, we choose NAUNet, which is a strong baseline on medical image segmentation. It has adaptive model design and hyperparameter search for each specific dataset. And it's fully supervised. There is no meta learning, no disentanglement. And the second one is SDNet with augmentation. It's semi-supervised with disentanglement, but there's no meta learning. LDDG, it was a sort on SCGM dataset, but it's not meta learning approach. It's fully supervised. It has feature alignment and regularization for domain-generalisation. And finally, SAML is fully supervised. It has meta learning. There's no disentanglement. For qualitative results, you can see here for MMS dataset, our model performs consistently well for all the cases with different percentages of labeled data. Similarly in SCGM. So you can see here, even in the extreme case with only 2% of labeled data, our model can still extract meaningful segmentation mask, but other models fail. For quantitative results, of course, we can do better consistently. So you can see here, comparing our model with supervised meta learning approach SAML, our model can perform well for each case. Similarly, in comparing our model with semi-supervised approach SDNet with augmentation, no meta learning, our model can perform consistently better. So to conclude, our model is the first semi-supervised domain generalization framework. It combines meta learning and disentanglement for medical image segmentation. And we propose to use low-rank regularization to encourage better disentanglement and generalization performance. We achieved the sort of performance in a low annotated data region on 2 medical datasets, and also show how disentanglement can help for domain-generalized medical image analysis, even with less annotated data. And finally, check out our paper also at MICCAI 2021 oral representation, controllable cardiac senses with disentangled anatomy arithmetic. So basically, we generate new plausible images with novel anatomy structures for domain generalization. Thank you founders. Check out our paper and also the GitHub repo. Also, feel free to check our group website.